Okay, that's good.
Just like enjoy it.
So, I'm not going to do anything terribly exciting today. It's more of I'd say preliminary or prerequisite knowledge. You probably know most of what I'm going to tell you today already, but I just want all the rules to be at the forefront of your minds and just we're all on the same page. So let's just suffer through this for a moment. We're actually going to do a review of exponential.
Oh, thank God.
And
That first section tripped me up yesterday.
logarithmic functions. Right? Okay, let's start with exponentials. So be aware of the notation. Say like x to the a. So the thing up here, it's called an exponent. Or it's called a power. Of course, it's of x. And x is called a base in this scenario. Okay. So, example, we say x cubed. And so power is 3. Base is x. So x to the power 3. X cubed in this case. Some of them have nice numbers like x squared and x cubed. We all know that. Okay, so exponents. What I want to make sure that you remember is the laws of exponents. Let's do one. If you have two exponentials, they have the same base, and you multiply them, what happens? Yeah?
Don't you just add the exponents?
You add the exponents. So if you multiply things of the same base, you add the powers. If you divide things of the same base, you subtract the powers. If you have something to a power and you raise it to another power, you multiply the powers. Another thing you should be aware of is if you have something raised to the power of 0, what is that?
1.
Well, that's 1. As long as your x is non-zero. This also means your x is non-zero because you don't want to divide by 0. You actually use this to derive that, so you don't want division by 0. 0 to the 0 is undefined. 5. This one's kind of silly, but let's just write it down anyway. X to the first power is just x. 6. You should know that exponentials distribute across products. So if I have something times something raised to a power, I can actually distribute it. Remember, this does not work for sums. Like if there was a plus in between here, I can't do this. But with a product, with a multiplication, you can apply it to each. It also distributes across division. So if I have a division raised to a power, I can just raise each individual to that power. I think that's it. So I'm not going to give any examples because I think we've seen things like this before. But what if you have, say, a negative power? What does that mean? Yeah?
1 over x to the power of a.
Right, so you make a power negative, what it does is it takes the reciprocal. It doesn't actually change the sign of anything. 9. What if you have a fraction in the power? X to the a over b. Yeah?
It would be square root of x and then the b will would be on the outside of the square root.
the b root of
A,
x.
and a in the inside.
Right. Or take the root first and then raise it to a power after. These are interchangeable if your x is positive. Interchangeable. If your x is greater than or equal to 0. So that's one we're going to use all the time. So for example, x to the 1/2 is equal to the square root of x is a very famous one. X to the 1/3, also pretty common. You should know that that just means the cube root of x. If I say I had x to the 2/3, that means that's the cube root of x squared, and so on. Okay, so those rules you should just kind of know off the top of your head and be able to apply them in various contexts. We'll do a bunch of examples next time before moving on, but for now I just want you to know the rules. Let's look at exponential functions. The form of these is like y equals a to the x. Here, let's assume a is greater than 1 and a is a constant. So if you have the base as a constant and the power is a variable, and you can just plug in different x values, you give rise to what's called an exponential function. For example, y equals 2 to the x is an exponential function, or y equals 1/3 to the x is an exponential function, or y equals pi to the x is an exponential function. If y equals x squared, not an exponential function. So these are exponential functions. Right? The base is a constant and the power is the variable. And we can, of course, transform them. So I could have something like 3 times 2 to the x minus 1, and that's also an exponential function. So, right, this is just the quintessential example. So that's exponential functions. Let's look at the graphs. You should know what the graph of an exponential function looks like. So if you have y equals a to the x, and your a is larger than 1, its graph looks like this. Pass through 1 here, and it will approach the x-axis as you go on. It'll keep getting smaller and smaller and smaller, but it will never actually touch the x-axis. And this happens when your a is larger than 1. Now you might wonder, well, what if your a is smaller than 1? Well, notice here I can have y equals a to the minus x. That one is going to be a shift, a reflection. Or when you change the inputs to be negative, it's a reflection. And this covers the case where the base is smaller, let's see, between 0 and 1. So for example, if you have y equals 1/3 to the x, what would that actually look like? Well, by the laws of exponents, I know I could actually write that as 3 to the minus x. That's what it actually means. Right? Well, technically, you'd first distribute the power. 1 to the x is just 1, so you have 1 over 3 to the x, which you can write as 3 to the minus x. So you can think of that. Once you figure out how it looks for larger than 1, then thinking of a base between 0 and 1 is just a matter of reflection. And so we can deal with those bases as well. We don't really worry about negative bases. If it's less than 0, we do not consider negative bases in this class. There are other reflections that you should know about. So if you have y equals, you can negate the entire thing on the outside, right? So if your a to the x looks like this, if you take the negative, it reflects in the x-axis. That's going to look like that. And you can negate the outside and negate the input. And that's pretty much just going to reflect that one. That's going to look like that. So the main graph you should know, but you should also know about reflections of the graph. What else? There's a very important example. Does anyone know what I'm going to say? An exponential function that kind of stands out from the others. It's the function that we call e to the x. This is called the natural exponential function. We're going to be using this guy all the time. Very important, has a lot of applications, and as far as calculus is concerned, it's indispensable. E is a constant. Of course it is because it's an exponential function. It's roughly 2.7 non-repeating decimal. So no one has ever written down this number in its entirety because we haven't actually calculated all the digits. But it is relatively small. It's 2 point something, right? So it's less than 3. And it was named after a mathematician. He was a Swiss mathematician. Named Euler. A lot of people read that as Euler, but it's not Euler. It's Euler. It's Swiss. Okay. So. Euler was studying compound interest. And remember, that's like when money is growing according to this formula. So A here is the amount or balance in an account. P is the principal. So it's the original invested amount. R is the interest rate, written as a decimal. N is the number of times compounded per year. Right, so it's how many times you're adding interest on top of interest on an annual basis. T is time. and it is the variable in this case. So this gives rise to an exponential function. Right? So if you're trying to track the value of money that's growing according to compound interest, the value is going to start to grow kind of like in that shape. It won't grow like a straight line or anything like that. It'll grow like a curve like this. And Euler was considering a very specific situation. This question, if you have $1 and you're charged 100% interest rate, which is really huge, and compounded not every day or every hour, but an infinite number of times. How large would the balance be? After a year. So essentially, you look at the compound interest formula and you plug in 1 here, interest rate 100%, which is 1, so you plug in 1 there, you plug in 1 for time, and your n just keeps growing. So in other words, if you have the expression 1 plus 1 over n raised to the n, and then you let n go off to infinity, like you're doing it an infinite number of times, you keep adding interest on top of interest, what does this number get close to, right? So you can plug in different numbers here, plug in a million, plug in a billion, plug in a trillion, and actually calculate what it comes out to, and you realize that it actually gets closer and closer to that number. So it turns out that the answer to such a question is the value in the account will be roughly $2.72, which is very surprising, and it's going to be surprising for the next thing I'm going to mention. Because there are many reasons that one might expect under these conditions that you would owe an infinite amount of money at the end of this time period. But no, you actually wouldn't. You owe that much. And it turns out that this expression is somehow super convenient. It shows up in calculus and other places in mathematics in the strangest places. And so it's actually convenient to have a number that represents this pattern in this situation, and E is that number. Exponential functions. So that's another important fact. So you should know what an exponential function is in general, what the picture looks like. You should also know that e to the x, y equals e to the x is a very important exponential function. But the next important fact that you should know about exponential functions is that they grow fast. Relatively speaking. So exponentials change a lot faster. Than polynomial functions, which is the next most familiar kind of function that you would know of, and power functions in general. power function is kind of when you switch the situation from having the base is a constant and the power is a variable versus the base is the variable and the power is the constant. Now, does it actually really make a difference? Like if you look at y equals 2 to the x versus y equals x squared, are those things really any different? Well, yeah, in terms of the shape they're different. If you look at y equals, say, x squared versus y equals 2 to the x, and you can compare these two. Let's say, here's my x squared, it's a parabola. So here's my 2 to the x. So they're very different in terms of shape, but they're different in another important way. And here's how they're different. So this is a very important concept that we will return to, but I just want to, since we're here, just dump this factoid on you. Let's say we kind of increase the scale. Okay. So we're zooming out, right? And we're going on to very, very large x values. So the inputs are going off to infinity, right? So a cajillion, bajillion, quadrillion to a bajillion, right? Whatever number you want to make, it's huge, bigger than any number you can actually imagine, right? So let's say you zoom out. How would these graphs compare to each other when you actually zoom out? So here's your y equals 2 to the x. Okay. What do you think the x squared is going to look like? Maybe like... Okay, so if you zoom out, right, here's how they actually compare to each other. This guy is going to be so much bigger than that guy that guy might as well be 0. Might as well not even try. Don't even get up in the morning. You're too small. Like you don't even try, right? This guy here, they grow faster, and I mean a lot faster. I mean, if you zoom out, this guy is so big that guy might as well not exist. Like it's that much of a, it's crazy how big an exponential can get. So 2 to the x will outgrow x squared in spectacular fashion. X squared, relatively speaking, it's 0. And in fact, 2 to the x will outgrow any polynomial. Any polynomial. Even if you have x to the 1,000,000th power, it doesn't matter. Eventually, this is the situation you're going to find yourself in. X to the billionth power, doesn't matter. 2 to the x will be larger than that. Exponentials grow really, really fast. Right? Which, by the way, credit card debt grows like the red line. That's why people get in trouble, right? Your salary grows more like the blue line, and your credit card debt is growing like that. That's how people get in trouble. They don't really realize, because they look at their bank account and they kind of say, well, I can kind of manage things. Yeah, but no, if you let it go unchecked, things can really get out of hand. So that's a very important fact about exponential functions. Compared to polynomials, they grow very fast, very large. They get much, much larger. So, we can express this by, I can say something like, let's say x to the n if you compare x to the a with a to the x, then I can use this symbol to say a to the x is eventually much bigger. A to the x is eventually much bigger. For large x values. And here, like I said, we're assuming our a is larger than 1. So if you have an exponential function growing like that, increasing as you go off to the right, it will beat any polynomial. In fact, it doesn't even have to be a, it could be any number here. N is any constant. The exponential is going to be bigger, like by a lot. Right? That's something that we're going to return to. It's going to help us solve a lot of problems, just knowing how exponential functions relate to other important functions that we know about. So yeah, so originally when Euler was considering that question, we were like, well, you're adding interest an infinite number of times, the money's going to go off like that. No, it actually ended up at $2.72, and it was a strange thing to realize. So just limiting it to 1 year actually tames the function a little bit. But I'll use notation like that in the future. That's what it means. That weird greater than, less than symbol just means that eventually one is much larger than the other one. To the point where the other one might as well not even try. Let's move on to a cousin of the exponential, the logarithm. What is a logarithm? A logarithm sometimes just call it log for short of a number to a given base is the power in the sense of exponent. That the base must be raised to. Give the original number. So the notation, how we actually write this down, is you write log. The base is a little number that you put down here. You put the number beside the log, and this is the power. Right? So this is the base. You want to know what power do I need to raise this base to in order to get that number. So for example, we can determine log to the base 2 of 8 is 3. Why? Because I have to take the base 2, raise it to the power 3 in order to get 8. So I can write log to the base 2 of 8 is equal to 3. Right? Since 2 raised to the 3 gives us 8. So what are the laws of logarithms? That's what a logarithm is. Let's see how they work. So law 1 is pretty much the definition, what I just said, just write it in symbols. If you have log to the base a of b equals c, what that means is a raised to the c will give us b. Okay. These two expressions are they're saying exactly the same thing. So saying I can raise a to the power c and get the number b is the same as me saying the logarithm to the base a of the number b is going to give me c. And you might say, well, I was pretty happy with that. Why do we have to introduce this complicated notation just to go the other way? Well, notice that the log allows us to solve for the power. So if you have an equation like this, and you want to solve for the power, you can actually use a logarithm to figure out what the power is. You want to know what is c equal to. C is going to be equal to this. Now, why that is useful is that just kind of flipping things around like this can actually decrease the complexity of certain operations that we want to do. So for example, logarithms will turn powers. So let's say I'm logging something to a power. It'll turn that power into a multiple. You can move that power down in front. Multiplying by n is going to be easier than raising something to the nth power in general. So, example, if I have log to the base 5 of x cubed, that's the same as me saying 3 times log to the base 5 of x. I could take a power of something being logged and move it down in front. Another way logs make your life easier, law 3. Logs turn products into sums. So if I have a log of a product, x times y, it turns out that this is the log of x plus the log of y. So it will go from multiplication to addition, right? And adding two things and then multiplying two things. They turn divisions into subtractions. And you'll notice these are kind of analogous to the exponential rules, right? Having something raised to a power to another power is multiplying the powers. If you multiply things of the same base, you add the powers. If you divide things of the same base, you subtract the powers, right? These are all just looking at the exponential rules in from a different direction. Law 5 is called the change of base formula. It's the formula that allows us to change the base of the logarithm we're working with. Because sometimes if you're working with a certain base, it might be convenient for you to use another base. To introduce some other base, you can use this formula. So C is a conveniently chosen base. Let's do an example where this might be convenient. Example. Let's say I wanted to find log to the base 4 of 8. In other words, what power do I need to raise 4 to in order to get the number 8? So you might start thinking, oh, 4 to the 1 is 4, 4 to the 2 is 16, that's already too big. The answer has to be between 1 and 2, right? So exactly where between 1 and 2 you might not be able to guess at the moment. Is it exactly halfway between 1 and 2, something else? But instead what you can do is change the base, because 4 is not a very convenient base to work in if you're looking at the number 8. What would be a convenient base? 2. I actually know how to talk about both 4 and 8 in terms of base 2. I can introduce the base 2 by using the change of base formula. Log to the base 2 of 8 is 3. Log to the base 2 of 4?
2.
It's 2. The answer is 3 over 2. It's exactly 1.5. And you can check this, right? If you take 4 raised to the 3 over 2, by the laws of exponents, that's just the square root of 4 cubed. Well, that's just 2 cubed, and that's 8. That's the answer. So base 4 wasn't very convenient. Base 2 was a lot nicer. I could get to the answer by switching to base 2. Spoiler alert, e is going to be a convenient base for calculus. If I have a log in any other base, changing it to base e is going to be very useful. And I can use this formula and put like a base e here instead. And I can switch from any other base to Euler's number. And that's going to help us solve a lot of problems. Here are some other rules. Law 6. So the first 5, very important. The next, I'm going to give you 4 more. These are, it's good to know off the top of your head, but technically you can derive them from the previous laws. All the other laws can be derived from law 1, in fact. But something you should know off the top of your head is what is the log of 1? What do you think? What's the log of 1? Zero. Right? Why? Because a to the 0 is 1. Right? Remember, the log is the power I need to raise the base to in order to get this number. Raise a to the 0, you get 1. Right? A is some positive number. Right? What is the log of 0? A is some positive number, like 2. What power do you have to raise 2 to in order to get 0? Yeah? Hmm? What? No, she's right. It's undefined. Trick question. Log of 0 does not exist. Because there is no power that you can raise a positive number to get 0. You raise it to a positive power, it'll get bigger. You raise it to a negative power, that's just taking a reciprocal. You raise it to 0, you get 1. There's no number. If you have 2 to the x, you can't choose an x value that makes that 0. In fact, 2 to the x will never be 0. We know the graph of that. Right? It'll never actually touch the x-axis. So it's never 0. So log of 1 is always 0 no matter what the base is. But log of 0 is undefined. It doesn't actually make sense. Law 8. This says if you have a log and you plug into that log an exponential with the same base, what is the result? What power do I need to raise a to in order to get a to the x? X. If we have the opposite relationship is actually true. If I started with the exponential and I plugged the log into the power and they have the same base, turns out something very similar happens and you just have x. In other words, they kind of cancel each other, right? You take an exponential, you plug into the log, as long as they're the same base, they'll cancel each other and you're left over with the x. If you have an exponential, you plug a log into an exponential, as long as they're the same base, they'll cancel each other and you have that. Remember, the log was developed to kind of solve for the exponential. So it kind of is meant to cancel the exponential from one side of the equation. Law 10. This isn't really a law. It's more introducing notation. I mentioned that e is a very convenient base. So we actually have a shorthand for writing down log to the base e. Does anyone know what it is? It's ln. It's called the natural log. Sometimes you write that. It's the same as writing ln of x. So this is called the natural log because you're using the base from the natural exponential. If you have just log, where I don't actually write the base, we will think of it as meaning base 10. This is called the standard log. One thing is worth mentioning, just in case you're, this is context specific. So not writing the base can mean different things in different contexts. So in like high-level math and Wolfram Alpha, which I mentioned to you on the syllabus. Whenever you see LOG, it actually means ln. Right? Because in math, E is just, no one works in any other base, right? Once you're in math. If you're in engineering and say life sciences, then your LOG is logged to the base 10. If you're in computer science, so you're reading some computer science textbook and you see LOG, it really means log to the base 2, because base 2 is convenient for computer science, it's binary, right? So log just means the base is understood for context. The context might matter though. So depending on what source material you're reading, LOG might mean something different. But for us in this class, LOG means base 10. So if I don't write the base, I mean there's a base 10. If I write ln, I mean the base is E. Now, one thing I do want you to be aware of, a lot of times students get scared by notation. If something looks scary, they freak out. This is just a logarithm like all the other logarithms. Ln x works exactly like any other logarithm. It obeys the same rules, right? So it's just a change of notation to emphasize that we're using a special base. So don't think anything's gonna change here. So if I have ln of something to a power, I can still move that power down in front. If I have ln of two things multiplying, I can split that up into the sum of ln's, etc. Right? All the rules I mentioned before, they work with ln just like they work with anything else. Right? It's just a normal logarithm. So all the previous rules will work. In particular, if you have ln of e to the x, it's just x. And if you have e raised to the ln of x, that's just x2. Right? Because ln is base e. So those are things you should know. We're going to use ln. E and ln's. Very, very useful for math and science. What else? Laws 8 and 9 tell you something very important. The exponential function, a to the x, and the logarithmic function, log to the base a of x, are inverses of each other. Remember what an inverse function is? It's a function that undoes one function. If you plug one into the other, you just get the original input. That's what laws 8 and 9 told us. This means we can figure out the graph of a logarithm pretty easily. Because we know how to find the graph of an inverse function if we know the graph of the original function. So if we had our exponential functions like that, that's y equals a to the x. Then to find the graph of the inverse, do you remember how you find the graph of an inverse? You're reflecting the line y equals x. This is the line y equals x. And then you flip it over like a mirror. And once you do that, you obtain the graph of the logarithm. So this is what the graph of y equals log to the base a of x look like. It would also pass through 1 here, just like how that passed through 1. so that gives us the graph of a logarithmic function. So you have y equals log to the base a of x, where a is greater than 1. That graph looks like this. I want you to notice that log of 0 is undefined. It never actually touches, you can't actually plug in 0. Notice that you also cannot plug in any negative number. And again, we can do all those reflections. So I can take the negative of that guy, and that is just flipping it upside down. You can also bring the negative inside, means that it flips over here. You can also put negative both on the outside and the inside, and it would flip it like that. So this is the main graph. When you think of a graph of a log, this is kind of the picture that should come into your head. But you can shift it and reflect it just like any other graph. So exponentials grow like that. They will grow faster than any polynomial. Conversely, what you'll notice is that a logarithm will grow slower than any other polynomial because it actually takes that rapid growth and then flips it on its head, right? So that's one thing you can note. How different functions relate to each other is going to be very important. So what I can say here is that if I'm looking at x to the a, and I know how that compares to a to the x, and now I know how that compares to log to the base a. The relationship is like this. So exponentials are so big compared to polynomials that's like eventually this guy might as well not even try. He's like 0 compared to that guy. But the exact same relationship holds between polynomials and logarithms. Eventually, if I look at x squared, it's going to be so huge compared to log to the base 2 of x that this guy might as well be 0. So this guy's super big compared to that guy, and that guy's super big compared to this guy. And they kind of have this relationship. So you should kind of have that idea. It's an important idea which we'll return to in the future. But just having an understanding, exponentials are bigger than polynomials and those are bigger than logs. It's kind of a kind of idea that's going to be very useful. How things grow is going to be very important. It's one of the main reasons calculus was developed, just figuring out how fast things grow, how fast they change, how fast they move. And if you describe things by certain functions, you should know how they relate to each other. We will stop there for now. Next time we'll do some more computational examples, and maybe we'll move right into calculus right after that. No, you had a quiz yesterday.
No, I know, but I just didn't know.
No, quiz is once a week, so your next quiz is Tuesday. See you guys Friday.